we all know how the whole rest of the world uses metric system, right?
Yeah.
We all know the metric system sucks.
Yeah. It's so much better than this.
Stupid.
No,
It's my answer, and it's what I say it goes, so there. I've never been a fan. I know it makes sense, whatever, but this is kind of the same idea that the rest of the world also uses what are called radians. And radians are stuff built off of what we call the unit circle. And the way that we use these is that it becomes in terms of what we call in terms of pi. And we develop in such a way to show that radians, in this case, are an extremely easy unit and idea to work with, because it's all about, when we were talking about these reference angles, and it's all about the idea of bouncing a reference angle off of the x-axis. But we have to understand how that's put together. And these next few sections with the trig stuff, to me, I think is like the entire basis of Algebra 2. The better you get at this little bit, those are the people that just finished out in pre-calc with their trig units. We're like, oh, this was easy. And the pre-calc trig is not easy because, excuse me, they understood the idea of where this came from. They were able to build out of it. It's pretty cool how it works. So what I like to do is first define what we call some, how angles are defined. Oops. One of these days this will start working more. We talked a little bit about this when we were looking at the ambiguous case. We talked about what's called a terminal side of an angle. When you're looking at these, they call this the initial side, where the angle starts and where it ends. This part here is called the terminal side. It's where the angle stops. Okay. The terminal side of an angle can be in any one of the 4 quadrants. Angles are measured. We're going to start off in degrees today, just kind of talking a little bit about that. If you have a positive angle, we go counterclockwise. And if you have a negative angle, we go clockwise. All that means is just different direction. It's not that, someone was asking about this last hour, can you have a negative angle within a triangle? No, it's just placed in a different position. You're not going to have a negative 30-degree angle in your triangle, but what you could have is a triangle that has a negative 30-degree angle that has an ordered pair, XY coordinate there, which eventually, over the course of the next few days, we're going to work with a triangle like that. It's just showing that it's built into a different quadrant. Okay, does that make sense? It's just directional. I mean, remember, if you're moving backwards, you're just going another direction. It's just a negative way. Okay, that's all. When you have your quadrants, remember we use the good old Roman numeral system. And then Q4. Now, your angles can be lying in any one of those 4 spots. If they lie on an axis, it means that it lies on a quadrantal. It's called a quadrantal angle, which means it's either on the vertical axis or the horizontal
So
axis.
it's not considered to be.
It's not in a quadrant. It's on an axis. Okay. So like 90 degrees. 90 degrees is on the y-axis. It's not in either one of the quadrants. The minute you go 91, you're in the second.
So if the terminal is on.
Yeah. Yeah. That's how it goes. Your initial side will never start anywhere else besides 0, and it just works itself around. Okay.
Can we say that in the word?
Quadrantal. Well, we'll get into it more. We don't see a lot of it in this first section. We'll see more of it as we get into 13.3, probably sometime next week. Excuse me. So what we do here is we'll say that if I have a 130-degree angle, and I want to, yes, sir. Oh, you want to do that now?
Yeah.
Oh,
Oh, no, what do you want?
probably do it now, except I don't know if I'll be here the rest of the week.
Okay.
Just to get it, thank you, I didn't.
Whatever works.
So what I want to do here is I want to place this angle on the graph and figure out what quadrant it's in. And I'm going to start talking about a little bit more about what is its reference angle as well. When you're doing these things, remember it just goes real easy, 0, 90, 180, 270, and then 360 all the way back around. We've done that before, that's not a big deal. If I'm going into 130 degrees, that means I'm going past 90, and I'm somewhere in the second quadrant. So this is a Q2. Now here's the new thing that we're going to talk a lot about. It's called a reference angle. This idea of a reference angle, we talked about it briefly when we were describing the idea of how you can have the law of sines have what we call that ambiguous case, where you could have two different angles that have that same value for sine. The reason that was is because they shared the same reference angle. The reference angle is how far you are off the x-axis. Reference angles will always be measured off the horizontal axis. How far do you bounce up, or how far do you bounce down? Okay? So if this is at 180 degrees, how many degrees do I have to go up to get to the 130? 50. So this would be a 50-degree reference angle. Okay. Does that make sense? We're bouncing upward to it. Yeah.
Wait, does that mean that only 50 is a reference angle
Yes.
and 130 is not?
130 is the original angle that has a terminal side. That's where it's placed in quadrant 2. 130 has a reference angle of 50 degrees.
Oh, so
It's-
the reference angle is just like the other part of
Yeah,
this?
it's the supplement if you want it off of this one.
Okay.
Okay? It's how far are you bouncing off? All right? Remember, this idea of the reference angle comes into huge play as we start to get into what we call the unit circle. Because you have all of these different values, but they all have the same reference angle, just weird. Yeah.
So if it had just gone up, like, say, 20 degrees instead of over 130, the reference angle would be 160?
No, because it's only 20 degrees off that.
Okay, so the actual angle would be the reference angle.
Yeah, because it depends upon which quadrant you're going to wind up in. And you'll see that. We're just starting here, okay? There you go. All right. Like I said, terminal, initial, you don't have to worry about that. So let's look at these three quick examples. 210, -45, and 510. What I want to do here is draw them and place them in the correct quadrant. It doesn't say to talk about reference angle, but what I want to do is kind of get you guys in the mindset of always finding reference angles, because it's easier later. Okay? So if I'm going 210, excuse me, what quadrant do you wind in? Third one. There's my 210. Oop, not 2110. How far is this off of the x-axis? It's 30. It's 30 degrees off. Okay? So the reference angle here will be 30 degrees. But see how it's bounced down, so you have to come back up to it?
Yeah.
So when you're in the third quadrant, you're coming back up. Yeah.
So that means like it doesn't matter like that you went through the top two, like that doesn't matter.
Nope.
You just worry about the one that's in.
Yep. Your reference angle is always going to be between 0 and 90. It's always going to be between 0 and 90. It's always going to be a cube. All right. -45. -45, I'm starting at my initial spot at 0 and I'm just dropping down 45 degrees. I go this direction with my arrow of -45. What's the reference angle to get it back up to 0? 45. So its reference angle is, okay. There's a nice little pattern that happens here as far as whether you're adding or subtracting to go back up and down. Did you notice that yet? I'll show you this before we go to 510. If your angles are in these two quadrants, you're coming up, aren't you? You come back up. This comes up 30 degrees, this came back up 30 degrees. That's easily impressed. Here you had to go back down, and you had to go back down. So you were subtracting. Here you're adding. How do you get back up? It's little patterns that you'll notice that happen here. Okay? You don't have to base off of this. Just remember, how far are you off of the horizontal? That's how much you're bouncing. Okay? Those are what you're looking for. All right.
The rectangle is always,
The cube.
no, positive, right?
Yeah. Yep.
Okay. I'm like, it's not even, it's
510, put that on a separate one. This is where you have to do a little thing called addition. I know, it's tough. It's tough. I'm asking a lot here. If we start to go to 510, we spin around, there's 360. Do you agree? Go at another 90, how much is that? If I go another 90, it'd be too much, won't it? Somewhere in the second quadrant. Q2. And I heard you say that the next one around would be at 540. If I brought it, kept going around again. So what's the reference angle? Come back up. 30. It's got 30-degree reference angle. Okay. Which means that as you start to build into these things, no matter how many times you loop around the circle, whether you're going positive or negative, you're always going to have a terminal side that you'll be able to figure out how far are you off of the x-axis. Which means that you're going to get this. What's another angle that had a reference angle of 30 that's in the second quadrant? 150. 210 would have been in the third quadrant.
Oh.
Okay. So at 150, they had the same terminal side as 510 because it had the same reference angle in the second quadrant. That means they are co-terminal.
And then 360.
Correct. It's one more loop around. So every multiple of 360 degrees, you're going to always wind up with the same co-terminal. So 150 and 360 is 510. Get another 360 on that, that's what, 870? Go again, you get something, something bigger, maybe 360 more. All right, so every 300, or go in the other direction. If I keep subtracting it, if I keep subtracting around, if I subtract and I'm going this way, go negative. What would be negative off of that? You're going negative 180 to another negative 30, be negative 210. So negative 210 is just going the other direction.
How did that happen?
Physics.
That was so bad.
I just got water all over myself.
Oh, yeah.
Did you ever listen to what you wind up saying on the videos? I just got water all over myself.
Well, no. I never watched the videos unless I
I always watch
Now, what we've done here is work with what are called coterminal angles. And coterminal angles are nothing more than angles that have the same terminal side, that are in the same quadrant, that have the same reference angle. And you find them by adding and subtracting 300 multiples of 360 degrees. Really easy. Okay. Let me show you here. Coterminal, blah, blah, blah. Angles coterminal with given angle that can be found by adding or subtracting multiples of 360. We just showed that. It's crazy how I have this stuff set up sometimes. It's like I know what I'm doing. No idea. So let's look at one. Let's say we have 225. I want to put 225 on and graph it, and then I want to find a positive and one negative coterminal angle for 225.
That's going to end
That's all
up
it
in
is.
the third one.
It's going to end up in the third quadrant. What's its reference angle?
45.
It's got a 45-degree reference angle. We know that's 225. So it's within one revolution, correct? Since it's within one revolution, to get the two coterminals, just like you said, Claire, you add 360 and you subtract 360, and it gives you your answer. So one of them positive would be, what, 585?
Yeah.
And if I subtract 360, it's negative 135.
Sure.
Okay? And it goes through like that. All, excuse me, all we're doing is adding and subtracting multiples of 360. All right? Oh, that's fine. Is it always this clean and simple when it's within one revolution? Not really. Sometimes you have to go,
It's helpful.
well, what happens if your angle's 900 degrees? Yes, ma'am.
So the polynomial is the two numbers added and subtracted from 60.
360, yeah. What we're doing here is 585. If I graph 585, I go around, and I'd end up here. If I graph the negative 135, I just start here, and I wind up there. All three of those had that same terminal side with the same referencing, within the same quadrant.
Yeah, I'm confused by what you mean by one revolution, because like, if you go like more than, like.
Stand up. Go around one time. One revolution.
Okay, but.
Go around twice.
Okay, to be honest, I kind of lost count.
I did. That's why I was going, oh wait, was that one or two? That's all it means. But it's one within one revolution means one time around.
Okay.
You're between 0 and 360.
Does it change when it's two? Like, do you have to do something different than just add or subtract 360?
I wonder if I have an example.
Probably.
Look at the 495. We'll go to the negative. We'll do the negative one next. We'll do 495. If I yes, ma'am.
Will that previous
Add the 360 and subtract the 360 from the original angle. The original angle was 225, so it was within one full revolution between 0 and 360. When that happens, you just add and subtract, and those are your two angles. All right. If I'm at 495, that's more than one time around. You guys agree?
Yes.
So it's 360 and 135. You okay on that? So what quadrant did this wind up in? Quadrant 2. What's the reference angle? 45. It's got a 45-degree reference angle. Okay. Now, since this problem was more than one time around the graph, that's what I mean by it's over one revolution. We spun around-ish. Okay. We made 5 left turns. 5.5.
Oh,
Okay. So now, to find the other positive, you subtract 360.
Can you also add 360?
When you're finding reference angles, you're always going to find reference angles between 0 and 360 plus or minus. Within one revolution or within the other. Because since you're over one revolution, you don't continually spin, you unwind. Okay, does that make sense?
So if it's between 0 and 360, you're going to add
Add.
it, but if it's over, you subtract.
Correct. Yes, ma'am.
And then to find the negative one, you just subtract 720.
You just take 135 and subtract it again.
Oh, okay.
And then you're at 180 and 45, so it's negative 225.
So isn't that the same thing as subtracting?
But once you get the first one, you just go again. But you're right, it is 720.
So if it's over, you just do subtraction twice.
Yeah, and if it's over like 4 times, you have to do it a couple times to get it within that first round. That's all.
If it's under, do you add twice?
Yeah. And that's all it is. You want it to be within your references. You want to get them within that one revolution either direction. Okay. If you're more than one revolution to start, it's not complicated to go through that. It really isn't. Okay. If I'm looking at negative 60 as my starting point, does that change in terms of adding and subtracting? No. Now, am I going to subtract 360 from that?
No, you're going to add.
Well, I shouldn't have said it like that. Sorry. If I'm negative 60, I'm in the 4th quadrant, right? So to get the coterminal, I'd add 360 to that, which basically gets me to there, which is what? 300.
Yeah, 3 ton of.
So that would be at 300. Now, if I wanted to go another negative, since I started negative, you would just subtract another 360. And you'd be at what?
Negative 6.
You okay there?
That didn't work.
I didn't, and I think I was the only one that might have seen that. Wow. But your starting point, even though it was negative, was within 1 revolution. So you just subtract to get the other one. Okay? And all 3 of those angles all have the exact same reference angle. The reference angle for this is what? 60. Okay. Yep. The 300, the negative 60, and the negative 420 are all coterminal. They all have the exact same ending spot in the 4th quadrant with the same reference angle. Okay, it all works out the same. Which,
Why is it?
because geometry is doing a little bit of that.
Oh, really?
Yeah.
We never did
Yeah, you
that.
did.
We did.
Should have.
Did we? I didn't pay attention.
Which gets you to what are called radians. Radians?
Man, I hate circles. Did we talk about these last time?
No, I don't think you did.
I didn't pay attention.
You might have brought it up a little bit. Radians are measured on the circumference. On the circumference of a circle. And if your circle, you did arc length. You did that. Now, how do you find the circumference of a circle?
2 pi. You just read pi.
2 pi r. So it's 2 times pi times the radius. If your radius is 1, what's your circumference?
2 pi.
2 pi. So that means to go all the way around the circle is 2 pi. You okay on that?
Okay.
So here's what happens. If we're going around the circle,
Whoa.
So long.
Sick.
if we're going around the circle, you start at 0, 90, 180, 270, and we end up at 360.
If I draw a circle, it's an oval.
Now, as you're going completely around the circle, if the radius is 1, the circumference is 2 pi. You agree?
Yes.
Okay. So that means 360 degrees would have to equal 2 pi. 180 degrees is half of 360, isn't it? So it would be pi.
Oh, never mind.
2 pi. What? Make it larger.
You'll see.
Okay.
You'll see. We're just looking at the true rating. We're not measuring out anything here. Okay. So you're at 0. You're at 2 pi, 1 full revolution. Halfway around, you're at. Is that pi? What's that 90 then?
R. Half pi.
Half pi. Pi over 2.
Honestly, why?
90 is at half pi. It's pi over 2. Because between 0 to 90, or 0 to 180 is 1 pi. 0 to 90 is half of it. So then if between 180 to 360 is going 1 full pi, between 1 and 2 pi, what's halfway between 1 and 2?
1.5.
Or
3 halves. 3 halves.
3 pi over 2. Okay. All right. Let's get even weirder. 45 degrees. 45 degrees is halfway between 0 and 90, isn't it?
Yeah, right. So pi over 4.
Perfect. It's pi over 4. Very good.
Oh, smart.
All right, let's go reference angle. Go reference angle. Going 45 over here, going 45 up from 360 is what?
44.
Reference angle. Your reference angle is 45 degrees coming up off of the x-axis. That means your terminal side is at.
It's 135.
Very good. It's 135.
Aw, thanks.
So between pi over 2 and pi, between half a pi and a full pi is
1/4.
3/4 pi. Okay? Continue on. Going between 1 and 1.5.
Is 1 and 1.5. So that would be, so it's pretty easy. 1 pi over 4. No, never mind. No, pi over 4. It's pi over 4 again. 5.
5 pi over 4. 1.25. Okay?
Get out.
Now, we know that this degree measure, going from 180 down 45 degrees, what means I'm adding my reference.
So
So that's,
2, 5.
okay? And then lastly, if I'm just building off of 45 degrees, if my reference angle is 45 degrees into the fourth quadrant,
7 pi over 4.
7 pi over 4. And that degree measure was 45 less than 360.
So it's 215.
No, it's 1140.
I wish I was.
Oh my god.
That's just
So
so
that
bad.
makes
Does that make sense how it works in terms of just, all we're doing here is looking at it in terms of halvesies? Yes, sir.
I get them in terms of pieces of pie, so like whenever you go 1/4 pie,
Yep.
1 piece of pie.
And that's the idea. Here is 1/4 pi, 2/4 pi, 3/4 pi, 4/4 pi, 5/4 pi, 6/4 pi, 7 and 8/4 pi.
It's just confusing because you would feel like pi, but it's like pi.
Wow.
You know, I just thought about how that would sound on the video.
Now, for the angles, now I always like to build it out with quarters first because it's very easy to work with, you know, because all you're taking is half each time as you're going around. Now, it doesn't always work so clean. And we're going to come back, save this spot in your notes because I want to come back and add in the other couple other angles here in a second. But I want to show you how you convert from radians to degrees real fast. We can do that. In order to convert, it's kind of like a unit conversion, dimensional analysis going from feet to miles, you know, like feet per, or inches per second to miles per hour, things like that. How you have to do that, the multiplying your units drop out. Chemistry, yeah. It's kind of the same idea, but when we're converting from degrees to radians, you're going from degrees to radians, all you're doing is taking whatever your degree value is. For example, we'll do that 45, so we just did that. If I say 45 degrees, I multiply it by pi and I divide it by 180 degrees. Degrees divided by degrees, units drop, correct?
Yeah.
So then you get 45 over 180, which is 1/4. Why it's pi over 4. That's why it drops itself through, because the units drop. Okay. So if I want to convert 110 to radians, we never write it's pi over 4 radians. We just say it's pi over 4. Because it takes too much time. Remember, all you're doing for this is you take 110, slap a pi next to it, and throw it over 180. And simplify the fraction. What can you do? Cross off the zeros.
Cross off the zeros.
You get 11 pi over 18. You're done. That's how it simplifies itself out. And if you're going the other direction, instead of multiplying by pi over 180, you're multiplying by 180 over pi. So if I'm looking at starting with radians of negative pi over 9, that just tells me it's going the other direction. I multiply it by 180. What happens to the pi's?
Cancel.
They drop off.
And then you get, wait, don't you get 20?
Mhm.
Negative 20?
You're done. That's it. That's the conversion between the two units. To go from degrees to pi, or degrees to radian, you have to slap a pi next to it and divide by 180. To go the other way, you divide by, or multiply by 180 and divide by pi. Hopefully not. You're looking at it, you're ready to ask the question.
No, I'm just thinking deeply.
Make sure you can still stand up. So think of it. What's 30 degrees in radians?
30 degrees in radians is 6 pi. No, 6 pi.
6 pi. If it's 6 pi, we just went around the circle.
Pi over 6.
3 times.
Pi over 6.
You tried.
I was trying to think that.
All right, let's use that 30 degrees as a reference angle. If I use that 30 degrees as a reference angle and I go into the second quadrant, it means I'm coming up 30 degrees, which means this is at 150. You okay on that?
Yeah.
Now, here's where it gets interesting in terms of your fractions. Pi is 1 pi. Do you agree?
Yeah.
Is it the same as 6 over 6 times pi?
Yeah.
Yeah.
What's 1/6 left? Pi over 6.
I thought it was 15 divided by 18. Oh, it's the same thing.
Notice, I'm bounced up 1/6. So what's 1/6 less than 6/6? 5/6.
Yeah.
If I bounce down,
Yeah,
It's 7/6.
oh, yeah.
which is at 210. If I do that in the fourth quadrant, it's crazy, isn't it? But it's not difficult.
Thinking.
If I bounce down into the fourth quadrant with a reference angle of 30 degrees, I'm at 330.
9 pi. I win.
Do you?
And careful, it's not 9 pi over 6.
I didn't say that.
If I'm going around the whole circle, it's 2 pi, right? Same thing as that is 12 over 6, so it'd be 11 over 6. Okay? Because it's bounced down 1/6.
I forgot you have to do, okay,
Okay?
yeah.
Now, what I want you guys to see here is that you didn't need to do any of these conversions on your own. All you did was bounce the reference angle into each of the 4 quadrants. That's how this is built. 60 degrees. 60 degrees. When you go up 60 degrees,
It's gonna be.
it's 60 pi over 8, or 180.
3.
So it's pi over 3, good. So your reference angle is going to be pi over 3. So in the second quadrant, if my reference angle is at pi over 3, means I came up pi over 3, 120 degrees. Now, pi is the same thing as 3 pi over 3. Do you agree? What's 1/3 less than 3/3?
2/3.
It's 2 pi over 3. What's 1/3 more?
The 1 pi over 3. Wait,
4/3.
Yes, 3. Yeah.
And that's at 60, so that's what, 240. Okay. And lastly, going in, what's 1/3 less than 6/3?
5.
And then that was at, where were we at, 160, so that's 300.
The side of that circle is tricky.
Yeah, it's not the greatest circle, but
Trippy.
now, believe it or not, it's gonna be tough to believe here. Everything that we do for the next month or so is built off of everything on this circle.
Great.
Because in this quadrant, your x and y values are both what? They're both positive. Positive x, positive y. In the second quadrant, they are negative and positive. Here they are. And then lastly, it's okay. Now here's what I want you to watch. This is where things get really crazy. These two guys are the same reference angle, aren't they? Think about what we did with law of sines. When you had law of sines, if you had the same reference angle in the first 2 quadrants, what value, your x's or y's, stayed the same? The y value, because the sine of both 30 degrees and 150 is the same. So these two guys share the exact same y value because they're horizontally across one another. These two guys share the same x value because they're vertical from one another.
Okay.
These two guys also share the same y value because they're horizontal from one another. And then these two guys share the same, which means these two angles have the same cosine. These two angles have the same sine. These two have the same cosine, and these two have the same. And it's all built off of reference angles. So when you're doing these triangles, and we're working with the trig and trying to figure out where all this is coming from, it comes from three little angles. 30, 60, 90, and a 45, 45, 90 triangle. And that's how all of this is built. Every single reference angle that comes out of that, and it just mirrors itself within each quadrant by using those. Okay? It's pretty crazy how that works, isn't it? It takes a little getting used to, but you'll have to trust me is that once you understand it, people ask this all the time, do I have to memorize all of this? Because this is the unit circle. This is what we deal with tremendously. No. All you need to know is this, and then their cosines and sine values. Once we get into that a little bit more, it's so easy how everything's replicated if you can find reference angles, if you can find coterminality. Okay? Kind of a lot, but it's a lot of fun. This stuff's cool. We'll finish. I think we'll stop there. So, what is this, 13-2?
Yes, C.
I'll get you guys a blank one, because like I said, we're going to keep building a little bit more and more and more out of this.
I could make mine graphics class. That's really cute because it's really oh, nice. Oh, no, better class.
Let's start with that for now. All you're doing is finding coterminal angles. When it says to find the coterminal or draw the given angle, do me a favor, take an extra second and find the reference angle real fast. It doesn't take long, but it is something that you're going to get really good at, so you might as well just do a little practice with it. And then it's just converting from radians to degrees or degrees to radians. It's not a lot. There's a lot more stuff involved here, but we'll get into it as we keep going. I don't know. There is, so shake, rattle, and roll, and hide underneath your desk.
Wait, do we get to flex out first?
No,
I just work here.
Oh my god, okay, I've been trying.
I try not to pay attention to it as much as.
I just work here. That's a good one.
Patent pending, you can't use that unless you pay me money.
I'm gonna use that in my house. Should someone will be like, can you clean the kitchen? Just
In this